Hey, Rushadia. So, last night I had a great party at my place. There was a lot of leftover pizza. So, today morning I just grabbed the slice, popped it into the microwave, and 30 seconds later, there was one problem. I just realized the pizza was covered with ants. But that was not the only problem. Somehow the ants were still alive. How? How do ants not die in a microwave? Okay, so first let's understand how a microwave actually works. How does a microwave heat up food? So, first let me explain. Inside a microwave, something is emitted called microwaves. Now, what are these things? Now, microwaves are nothing but something called electromagnetic radiation. Now, don't feel scared of the word radiation because even radio waves are a part of the electromagnetic radiation. X rays as well, gamma rays, as well as visible light. The thing that differentiates all these from each other is something what we call, let me get another pencil for this color. Orange will do. What we call is frequency of the wave. Now, what is this frequency of a wave? Now, let me explain this with an example. Let's take the frequency, or let's take an example of a violin. So, let me just draw a quick violin. Actually, let's just call this a guitar. I think it's easier for me to draw a guitar. Okay, and this one string for now. Now, when we pluck this particular string, let's take this as a string, it vibrates up and down, and it vibrates up and down at a particular frequency. So, what is it? The number of times it goes up and down in 1 second. It's called the frequency of that particular wave. So, for example, the A string in a guitar has a frequency of 110. That means in 1 second, the string is moving 110 times up and down. So its wave is 110 hertz per second. Now, hertz is named after Heinrich Rudolf Hertz, the scientist who basically discovered electromagnetic waves. Now, getting back to these microwaves. Now, microwaves, as I said, are a part of the electromagnetic radiation, but they have a frequency of 2.45 gigahertz. Now, gigahertz is nothing but a hertz followed by 9 zeros. So, it's a big number. So, it's easier to write it as 2.45 gigahertz. Now, there's a very unique characteristics of this frequency waves. Whenever a wave of this frequency hits a molecule of water or a molecule of fat or sugar, it tends to make these molecules rotate and move around at a very high rate. This constant rotation and movement between them causes a lot of friction, and this friction is given out as heat, and that is what makes the food in your microwave hot. So, what makes ants so very special? Like every other living organism on this planet, ants also do contain water molecules. So, what stops them from getting their insides boiled? Could it be their exoskeleton? Could it be that it's a material called chitin? So, could it be that chitin reflects microwaves? Well, I did some research, but nah, it's not so. It lets microwaves pass right through. In fact, most insects on the planet have an exoskeleton of chitin, including shells of crabs and lobsters. So, if you had any idea of like wearing a crab suit and going inside a microwave to test it out, uh, plan otherwise. Now, let's draw the microwave again, just to explain this a bit better. Let's draw the walls of the microwave, the wall of the microwave oven as well over here to understand. Now, a microwave are something called standing waves. Now, why standing waves or stationary waves? I will just explain it out. Now, see, this is the source of the microwave in the oven. Source. It travels this way in this fashion. It hits the metallic wall on the left hand side and it reflects back in this particular way. When it reflects back all the way back to the source. Now you see this movement, this wave going up and down over here. It goes up and down in a standing fashion or like a stationary fashion, just like a guitar string. Imagine if this was a guitar string over here and these were the two nodes, the bridge and the neck. It would go up and down in this particular fashion, exactly the same as a standing wave or a micro inside the microwave. Now these intersections are called nodes and the highest point is called the antinode. The node is where the energy level is at 0 and here the energy level inside the microwave is at its maximum. So what you see, the energy level starts to increase from the node till the antinode and from the antinode it starts to decrease back to the node. So what we realize is inside a microwave, there are a lot of hot spots and cold spots, as you will see. The heating inside a microwave is not constant. It's not the same. So that is why inside a microwave we have a table that rotates. So when the microwave goes inside, we have food that goes around the table and basically heating it evenly around. Otherwise, without this table, we would have uneven heated food inside the microwave. Now, let's get back to the ant. Now, the ant has a very unique characteristic and takes advantage of this. So let's draw a nice big ant to explain this better. Now, why have I drawn this big ant? Just to understand, there is a lot of surface area on this ant. In fact, the surface area of the ant is far larger than its volume. So its surface area to volume ratio is extremely high. Now the characteristics of a surface area to volume ratio, when it is high, the ant loses a lot of body heat very quickly. All animals with a high surface area to volume ratio lose energy or lose heat very quickly. So even if an ant inside a microwave is at this spot over here, let me take the orange pencil, is at this spot over here, a very high energy spot, high energy. What we realize is the table is moving. The ant is also moving as well. So it very quickly gets away from these areas into the lower energy zones and it loses its body heat as well very quickly. So the ant does not stay in a high energy zone inside the microwave for too long in order for it to get injured or die. And that's why the mighty ant survives inside a microwave.